So again, if you're adding up positive integers from 1 to n, this is the formula that gives you that sum. So, for example, let's say you're going to have this. So we sum integers 1 to 65. So what you could do in this case, n, what's going to be 65. So the sum, n times n plus 1, divided by 2, will be 65, 65 plus 1, divided by 2, or 65 times 66 divided by 2. And let me get my calculator out here real quick. It'll be 2,145. So any questions about that? All right. So another thing you could have you have the sum of even numbers 2 to 50. So what that means is you're going to take 2 plus 4 plus 6 up to 48 and 50. Now what you can do in this case, we can factor out a 2 since these are all even numbers. And you have 2 times 1, 2 times 2, 2 times 3, 2 times 24, 2 times 25. So each of these is a multiple of 2. So you can factor out that 2. Now what we can do, we can use the formula on the sum that's in the parentheses. So in this case, n is going to be 25. So you have 25 times 25 plus 1 over 2. And these 2's, you could say they cancel, but if you don't see that they're going to cancel, that's all right. We can do the computation fully on the inside, again, following our PEMDAS. So here, 25 times 26 divided by 2. And we'll get 650. questions about that? All right. So another type of problem.
I'm sorry, I wanted to check really super quick, like the
Oh,
reason
sure.
why you took it to, oh, I see what you did. So you're,
So what you can do, if you factor out a 2, you'll get a sum instead of 2 to 50, where you're only adding even numbers. You'll get a regular sum of all the integers or positive integers from 1 to 25. And then you can use that formula. So hopefully that helps. Now let's take a look at some of these other problems. All right, so this one always comes up. Ducks and pigs. So the number of ducks and pigs is 35. So you have 35 ducks and pigs in a field, and each duck has 2 legs, and each pig has 4 legs. I'm just going to wait just a few minutes here, or maybe a minute or two. I think a student has dropped off the Teams meeting. So I'm going to see if maybe that had something to do with like a computer crash or something like that, which happens. Mine did that the other day. So give a little bit of time to do a quick research on something. So if you're wondering what I'm doing, I'm just looking, I'm trying to verify a formula. All right. Well, I'm going to continue for now. So we've got these 35 ducks and these pigs in a field. Each duck has 2 legs and each pig has 4 legs. So the total number of legs is 98. So how many ducks and how many pigs are there? So you have 35 ducks and pigs. Each duck has 2 legs, each pig has 4. The total number of legs is 98. How many ducks and how many pigs are there? Well, what we're going to do, this is going to turn into what we call a system of equations. And so the way it works is this. Let's let D be the number of ducks. So if we're following our process, our 4-step process, you can kind of think this is number 1. And now we're going to kind of do it a little bit backwards. We're looking at what's unknown. So what do we not know? Well, we don't know the number of ducks. And we don't know the number of pigs. We'll let P equal the number of pigs. And so then let's take a look at what we do know. So we have what we don't know. What do we know? Well, the sum of pigs and ducks is 35. We also know the sum of legs is 98. Each pig has 4 legs. Each duck has 2 legs. So what can we make of this? Well, what we can do is we can take this, the sum of legs is 98. We know the sum of pigs and ducks is 35. So what we can do is this. If D is the number of ducks and P is the number of pigs, well, then the plan I'm going to try to go with, and I mentioned it earlier, is the system of equations. The number of ducks plus the number of pigs, that has to be 35. Now, let's think of this in terms of legs. So duck legs. Well, each duck has 2 legs. So that's going to be the total number of duck legs is each duck times 2, because each duck has 2 legs. And then for pig legs, well, each pig has 4 legs. So the number of pigs times 4 will give us the total of pig legs. Now, if we take the total number of duck legs plus the total number of pig legs, that's going to come out to 98. And that's the total number of legs. Or 2D plus 4P is 98. Now, how do systems of equations work? Well, what we're going to do is we're going to use the fact that we can replace one of these variables with this. I'll show you how. So let's take a look. And this, we're in step 3, we're carrying out our plan. We have d plus p is 35, and 2d plus 4p is 98. So what we can do, there are different ways you can solve a system of equations, but one thing we can do is we can solve for d. I'm going to subtract p from both sides. And this is sort of where that section where we would solve a formula for a variable, this becomes a very powerful skill. So we're going to take this formula, d plus b is 35, solve for d, and we're going to get this. Now what this says is the number of ducks is the same as 35 minus the number of pigs. So now I go to the d here. Replace the d with that. Now what's important about this, and this is sort of what I've kept my eye on, now this equation has only one variable in it. All we can do is solve for a variable when we have 2 in the equation, but if we can replace the variable with something that has a p in it, then we can solve for p, and p will be equal to a number. And that's what we're looking to do. So we can distribute this too. I'll give us 70 minus 2p plus 4p equals 98. If we gather like terms, 70 plus 2p equals 98. And now we just solve for p. Then divide both sides by 2. Get p equals 14. And so that's the number of pigs. Well, we're not done. We know pigs. We also need to know ducks. So let's go back to this first equation. Ducks plus pigs is 35. We substitute for p, replace p with 14. Ducks plus 14 is 35. Then we'll subtract 14 from both sides. We'll get ducks is equal to 21. So we have 14 pigs, 21 ducks. Well, is there something we can do to check it? Well, there is. We need to make sure that p plus d equals 35. Or 21 plus 14 that going to be 35? And sure enough, it is. So it works. Now there's another check we can do though. Let's check this. Is 2D plus 4P equal to 98? Or is 2 times 21 plus 4 times 14 equal to 98? Or 42, let's see, it's going to be 56. Is that going to be 98? And sure enough, it is. And so we have our answer. All right. So let's see, here's a good one. Again, some of these problems, you got to be a little creative. But one of the tricks for some of these is not to try to tackle the whole thing. Try to solve a smaller version and look for a pattern. So let's say we want to find this. Determine the ones digit. Let's go 4 to the 300. So what do we do with this? And I know what some of you were thinking. It's what I was thinking. We'll just put this in a computer, put it in a calculator. It'll give us the answer. We're good. What you're going to find, it's going to give you a truncated example, if it gives you anything at all. It's going to give you truncated answer, or if it doesn't give you an error. So here's a trick with this. What we're going to look for is a smaller pattern, or smaller problems pattern. And what we can do is compute the first few 4 to the ends. I'm going to compute the first few of these and look for this pattern. So let's start with 4 to the 1. Well, that's going to be 4. Let's go 4 to the 2. It's going to be 16. 4 to the 3. 64. Let's go 4 to the 4, and it's going to be 256. 4 to the 5. Let's see. 1024. 4 to the 6. 4096. And we could keep going. But we want to find out the ones digit for 4 to the 300. Now here's the thing to notice. We're interested in the ones digit. So the ones digit here is 4. The next one digit, pardon me, I'm just getting a different pen. So we have 4. the next ones digit is 6. The next one is 4, then 6, then 4, then 6. So working with just the first few of these, do we see a pattern? Well, there's a pattern where the ones digit alternates from 4 to 6. So it just does this the whole time. And we might even see another one. If you look at the odd exponents, what's up, that one there? Looking at the odd exponents, the ones digit is equal to 4. And for the even exponents, the ones digit is equal to 6. So when we go to 4 to the 300, 300 is an even number. So what this says, the ones digit of 4 to the 300 is 6. So the trick to this one, it's looking for a pattern in a simpler version of the problem. All right. So let's try another one. Let's say I have something like this. Well, we've kind of a step forward to the last question. We can use what we learned from that question and apply it here. We can use it for this future question. So we'll do the same thing. 7 to the 1 is 7. 7 squared, or 7 times 7, is 49. Now, 7 to the 3, get my calculator here, 343. 7 to the 4 is 1372. 7 to the 5, 9604. 7 to the 6, 67228. 7 to the 7, 823 543. 7 to the 8. Seven to the 9. Hoping something's gonna jump out here. 403 53607. 7 to the 10. 2 8 2 4 7 5 2 4 9. Now hopefully we're seeing something. 7 7 9 9. Maybe this is repeating. 7 to the 11. Right, really small. 1 9 7 7 3 2 6 7 4. Is it a 3? Yes, it's a 3. So 793 793. 7 to the 12. Ooh. And I'm going to start. Oh, I still have some digits. 2 2 and 2. Can I do it again? And I think my calculator's not going to let me go any farther. It's going to start truncating answers. So going as far as I can, does it look like I've got a pattern? There's a 7. There's a 7. 9 9 3 3 2 2. And if I could go farther, it'd be 4 8 3 1. So ideally, if I could keep going, and let me check something. I think I made a mistake. I think I miscounted something here. Let me double check my numbers here. I think I made an arithmetic mistake. Ah, there it is. Sorry about that. Made an arithmetic mistake. 2401. And this would be 16807. I apologize. Somehow I put in there's some mistake that I put in there. So it shouldn't be quite this wild. I have to admit, I was getting a little worried there. Like, oh my. And then let's go 7 to the 6th. Seven to the 7. And 7 to the 8. Excuse me. Excuse me. All right, this is better. We actually get to see a full cycle. But we've got 7 and 7. I apologize. I must have input one key wrong, and that threw everything off. So the lesson is, if things start getting a little weird, like, this doesn't seem to be, that doesn't mean that it's not that you don't have a long pattern. That could be the case, but again, double check your calculations. It's easy to make a little mistake, and it's going to throw everything off. So let's take a look at this. 7 to the 1, 7, 9, 3, 1, and then we repeat 7, 9, 3, 1. So what's going on here? Well, we got this pattern of 7, 9, 3, 1. Now what I'm going to do is I'm going to write out the exponents and the number or the ones digit that goes with that exponent. So here's our exponents. Seven, 9, 3, 1. These are the ones digits. We start again, 7, 9, 3, 1. And then we're going to keep going. And what's going to be the one digit for 1, 4, 6? Well, here's the idea. Every 4 numbers, we have a full cycle. So if we have numbers, exponents 1 through 4, we get 1 full cycle. If we have exponents 1 through 8, we get 2 cycles. And if we did 1 through 12, we would have 3 cycles. So here's the idea. Every 4, we get a cycle. So let's answer a question. How many full cycles are there from 1 to 146? Well, that's basically asking is how many times does 4 go in the 146? So what we can do, we can take 4 into 146. So 4 goes in the 14 at most 3 times. 3 times 4 is 12. Subtract is 2. Bring down the 6. 4 goes in the 26 at most 6 times. 6 times 24 is 24. I'm sorry, 6 times 4 is 24. You get a remainder of 2. So what this says is this. 146 is 4 times 36 plus 2 extra. So what we have, there are 36 full cycles. We have 46 full cycles. So what does that mean for us? Well, every time we complete a cycle, we then start over again. I'm just pulling up my cycle here. Okay. So this means we run through this cycle seven, 9, 3, 1, 36 times. But we have 2 steps left over. Those 2 steps will form a partial cycle. So if we have our 7, 9, 3, 1, 7, 9, 3, 1, 7931. This would be cycle 35. This would be cycle 36. And then, ooh, it's going to be 36. And then we have 2 left over. So what we could think of, and let me label it a little differently, because I think I'm losing the exponents here. So remember, these are all the ones digits. So let's see here. What this is saying, if we have 36 full cycles, that takes us to 144 for our exponent. So the exponent, 146, is 144. These are full cycle. This is going to be 144 plus 2. And this is going to be the 36. Full cycles. So that says, if we say this is 144, and this would be 143, 142, 141, this would be 145 for the exponent 146. So the answer is actually going to be 9. Now there's a less complicated way of putting this. I could sum this up into kind of a shortcut. And that might be a little more helpful. So let's summarize this in kind of a shortcut. We can take the cycle length. So we figure out our cycle is going to be 7931. The cycle length is going to be equal to 4 because we have 1, 2, 3, 4 digits. These are all the ones digits that we cycle through. So then we take the exponent, 146, we divide it by the cycle length. And we found out this was going to be 36 plus a remainder of 2. It's the remainder that's going to be important. So we go through this cycle all the way through 36 times. And then we have 2 steps left. So we actually can ignore the 36. And we just need to look at the 2 extra steps. First extra step will get us started on the new cycle, a second step into the new cycle, but then we're done. We're out of steps. And so that means the answer is 9. So basically you find your cycle, determine your cycle length, divide that into the exponent. You could ignore this number, but the remainder, that tells you how far into the next cycle, once you've gone through all these, how far into the next one you go. And then that's it. Questions about that, please let me know. All right. Let's see. So another one that has kind of an interesting technique to it. Let's see, I'm looking for change for a quarter. how many ways can you make change for 25 cents? And we're going to be limited to dimes, nickels, pennies. Now, again, we can think of this in terms of knowns and unknowns. And so what do we know? Well, we do know the total for any combination of these coins is going to be 25 cents. And we know the value of each coin. A dime is 10 cents. A nickel is 5 cents. And a penny is 1 cent. So what do we not know? Well, we don't know how many combinations of dimes, nickels, pennies, sum, pardon me, to 25 cents. Well, I mean, fair enough. I mean, that's what they're asking us to do. But there's something more fundamental that we don't know. We don't know what these combinations actually are. What are each of these combinations? And so it's discovering what each of these individual combinations are that's going to help figure this out. So let's do that. And so one way to come up with these combinations is to do a chart. So we're going to chart the combinations. And so we're going to go through with it. So let's come up with the chart. Let's say D for dimes, N for nickels, P for pennies. And each combination has to add up to 25 cents. Now I'm going to use a systematic approach. Let's say we max out the number of dimes. So to put together 25 cents, we can have at most 2 dimes. If we have 3, we'll have 30 cents if we've overshot. So we have 2 dimes. Why do we need to get 25 cents? Because 2 dimes is short of 25. Well, we could do it with 1 nickel. So 2 dimes and a nickel would give us 25 cents. But we could also do this. Oh, you have 0 pennies. We could do this with 2 dimes, 0 nickels, and 5 pennies. So with 2 dimes, those are the options. And that's it for 2 dimes. Let's go with 1 dime now. Well, as you kind of noticed, I went with nickels and then I went with pennies. And I'm going to do the same thing. If I have 1 dime, can I max out the number of nickels? Let's try to do that. And if I do that, well, that's 10 cents. I need 15 cents more. So 3 of those, no pennies. Or go with 1 dime. Let's reduce the number of nickels by 1. And you might begin to see a pattern here. So this is 2 times 5 is 10, plus 10 is 20. So we need 5 pennies to bring it to 25. Let's still go with 1 dime. 3, 2, 1 nickel. Well, this is 10 cents, 15 cents. Need 10 cents more. Need 10 pennies. And then finally, with 1 nickel and 1 dime, 0 nickels. So you kind of see a pattern. 2 dimes, 1 nickel, 0 nickels. Fill in pennies if we need to. For 1 dime, 3, 2, 1, 0 nickels. We're going to fill in pennies as we need to. 10 cents and 15 cents will give us 25 cents. Now let's go with 0 dimes. Well, we could get 25 cents with 5 nickels, 0 pennies. Or we could go with 4 nickels and 5 pennies. Or 3 nickels, 10 pennies. Or 2 nickels, 15 pennies. Or 1 nickel, 20 pennies. Or 0 nickels, 25 pennies. And that's going to exhaust all of our combinations. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 ways to make change for a quarter. Using pennies, nickels, and dimes. Any questions about that? Oh, keep forgetting. This is recording, so any questions, let me know. Well, all right. Well, I think that's about it. There's one question I think I would give a hint on. And again, if you have any questions about it, let me know. But let's say we have this. How many squares are there? Oh, I mean, there's just one. Only one square. But let's say we have this, though. How many squares do we have? And this is kind of tricky. 1, 2, 3, 4. So you have 4 small ones. And we have this one big one. So don't forget, this whole thing together makes a square. Let's take a look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9. But we also have this. This is a square. This is a square. This is a square. And this forms a square. So we have 4 medium-sized squares. And then we have 1 giant square. So here's my hint. This is 1 squared. This is 2 squared plus 1 squared. We have 3 squared plus 2 squared plus 1 squared. And that's all I'm going to tell you. Now, if you have questions about this, let me know. I'll be more than happy to work with you on it. But just want to throw this hint out there. Well, that's really going to be it for today. If you have any questions, let me know. Other than that, have a wonderful day. And again, let me know if you have any questions.